Glucose production in the liver is a coordinated process between glycogenolysis and gluconeogenesis. Glycogenolysis breaks down glycogen, providing glucose from glycogen stores, whereas gluconeogenesis will use smaller molecules as precursors like pyruvate, lactate, glycerol, and other carbon skeletons derived from amino acids to produce glucose. Both of these pathways, glycogenolysis and gluconeogenesis, are more active in the fasting state. The common molecule produced from gluconeogenesis and glycogenolysis is glucose 6-phosphate. The liver is unique in that it has glucose 6-phosphatase, which will produce glucose from glucose 6-phosphate. Without this former enzyme, glucose would not be produced from glucose 6-phosphate and could result in severe fasting hypoglycemia. In glycogen metabolism, pKa can phosphorylate glycogen synthase, and in doing so, it will inhibit the enzyme and glycogen synthesis or glycogenesis will be inhibited. On the other hand, pKa will phosphorylate the glycogen phosphorylase kinase, which in turn will be activated and can phosphorylate glycogen phosphorylase and activate the latter enzyme for the hydrolysis of glycogen. In gluconeogenesis, there are 3 enzymes that are upregulated by glucagon. These key enzymes are PEP carboxykinase, fructose 1,6-bisphosphatase, and glucose 6-phosphate phosphatase. All 3 enzymes are upregulated, or the expression of all these 3 enzymes is increased by glucagon. So gluconeogenesis becomes more active when glucagon is elevated in the plasma. Another important allosteric regulator of gluconeogenesis is acetyl-CoA. Acetyl-CoA in the liver will accumulate due to beta-oxidation of fatty acids by the liver. Acetyl-CoA in the liver will thus allosterically activate pyruvate carboxylase, a key bypass enzyme in gluconeogenesis. During fasting, lipolysis is increased due to the activation of hormone-sensitive lipase in adipose tissue. This is due to the phosphorylation of the enzyme by pKa, which is activated in turn by activation of the beta-adrenergic receptor by epinephrine. It is also noteworthy that tags stored in adipose tissue represent a significant amount of fuel reserves for various tissues during fasting, and the lipolysis of these tags and availability of circulating fatty acids is essential for maintenance of the energy needs of several peripheral tissues during the fasting state. The ketone bodies acetoacetate and beta-hydroxybutyrate released by the liver will provide an alternative energy source to multiple tissues, including the brain, muscle, and other peripheral tissues. It is noteworthy that ketone bodies are an important energy source for many peripheral tissues during fasting. It's important really to just appreciate the big picture about ketone bodies and how they're used and why they're important. So ketone bodies are derived from acetyl-CoA, and in turn that acetyl-CoA comes from the beta-oxidation of fatty acids in the liver. During fasting, the liver switches to beta-oxidation of fatty acids for its own energy needs. At some point, high energy molecules like NADH and FADH2 and ATP will start to accumulate. High NADH and ATP inside the mitochondria will inhibit the TCA cycle at the isocitrate dehydrogenase step, resulting in the accumulation of acetyl-CoA inside the mitochondria, which then can activate pyruvate carboxylase, the bypass enzyme in gluconeogenesis, and simultaneously will activate ketogenesis inside the liver. If you like this video, please subscribe. Thank you.